Welcome to my ASRU 2023 presentation. I'm Wang Yu from Shanghai Jiaotong University. This is the joint work of Shanghai Jiaotong University, Waseda University, and Carnegie Mellon University. Next, I will present the paper toward the universal speech enhancement for diverse input conditions. First, I will introduce the background of our research. It is commonly observed that existing speech enhancement approaches often only consider one or a limited range of input conditions. For example, considering sampling frequencies, some models are specifically designed only for 8 kHz and some are only designed for 16 kHz. In terms of microphone channels, some models are only used for single-channel processing, and some models can only do specific amount of multi-channel processing. On the other hand, some models only consider a single task that, for example, only do denoising or only do de-reverberation. Currently, there is no universal SE approach that can effectively handle diverse input conditions with a single model. In the research perspective, building a universal SE model that can handle arbitrary input is an interesting research problem. By building such a model, we can unify different SE tasks with a single model so that it is very easy to be used for different application scenarios. We can also improve the SE performance in realistic conditions, where both noise and reverberation, as well as other distortions, can exist along with speech. We can also utilize a large amount of data to train such a single model, and with very strong generalizability, which is especially important for downstream speech tasks such as ASR speech translation and spoken language understanding. So in this paper, as a step towards universal speech enhancement, we aim to devise a single SE model that can handle different input conditions without compromising the performance. So in this paper, we define the following input conditions that we wish one model can handle at the same time, including single channel, multi-channel with different array geometries, variable length, variable sampling frequencies, noise, and reverberation. Next, I will introduce our proposed model. We call our model unconstrained speech enhancement and separation network. Here, unconstrained means the model is not constrained to be used only in a fixed input condition. Instead, it is carefully designed for handling many different input conditions while maintaining the generalizability. The proposed model is mainly composed of 3 parts: the encoder, multipath block, and the decoder. The encoder and decoder are based on the STFT and ISTFT, respectively, and we project each time frequency bin in the STFT spectrum into an embedding for better modeling. The resultant 3D representation is then processed by the multipath block to generate the enhanced feature, which is finally projected back to the spectrogram, and then the waveform by the decoder. To achieve the independence of sampling frequencies, we adopt fixed duration window and hop sizes for STFT and ISTFT in the encoder and decoder. For example, we always fix the window and hop sizes to 32 milliseconds and 8 milliseconds respectively. Note that in contrast, in conventional speech enhancement approaches, they often set the window and hop size to a fixed sample length, which can correspond to different durations in different sampling frequencies. In our case, the corresponding duration is always the same, which means the window and hop sizes are adaptively adjusted according to the input sampling frequency. By doing so, the number of frames in the STFT spectrum will be always the same for different sampling frequencies, and only the number of frequency bins will be different, which scales with the sampling frequency. In other words, the time frequency resolution in the STFT spectrum will remain the same for all different sampling frequencies. This means that the relative information between adjacent frames or frequency bins is similar for different sampling frequencies. This is especially important because in this case, the model can easily generalize to unseen sampling frequencies. The only issue is that now the input feature has two variable dimensions. Both frequency and time will vary due to different sampling frequencies and different input length. So we need to design the backbone carefully so that it can handle this type of input. In the proposed architecture, the multipath block is used, which basically consists of transformer layers that conduct sequence modeling along the frequency and time dimensions independently. This design can naturally handle SDFT representations that have variable number of frequency and time sequences. Next, we also need to ensure the model is capable of processing input signals of different microphone configurations, including single-channel, multi-channel with different array geometries. Here, we adopted a well-designed TAC technique and inserted into the multipath block for spatial modeling. TAC, or transform, average, and concatenate, first projects the multi-channel feature into a hidden space, and then average the features from different channels. And finally, the average representation is then repeated and concatenated to each channel and projected back to the input shape. The channel-wise averaging operation makes the module independent of microphone numbers and permutations. Finally, we also hope that the proposed model have an approximately linear complexity with regard to the input signal length. Since transformer layers are used in the architecture, the complexity is inherently quadratic in the attention mechanism, which makes it difficult to extend for long-form speech processing. To address this issue, we propose to divide the input signal to short segments and use the memory tokens to pass the history information across segments. The memory tokens are a set of learnable tokens that will be updated by the model in an end-to-end manner. Inspired by the memory transformer approach in NLP, we utilize these memory tokens as a way to introduce recurrence in the transformer-based architecture. Specifically, we always divide the input signal into non-overlapping fixed-length segments. Then the model processes each segment one by one, with the memory tokens updated after each processing. And the updated memory tokens will be used for the processing of the next segment. In this way, the history information from the previous segment is maintained automatically by the memory tokens, and they can be implicitly utilized by the transformer layers in the multipath block via the attention mechanism. In addition, we further designed two independent groups of memory tokens to control the model behavior. When processing data without the need of derivative, we use the first memory token group. When processing data with both denoising and derivative, we use the second memory token group. This has shown effectiveness in our experiments, especially when combining data from different conditions for training the proposed model. We evaluate the proposed models in several different tasks. First, we evaluate the speech separation performance on the WSJ02 mix benchmark. All models are trained only on 8 kHz data. It can be seen that when evaluated on a mismatched 16 kHz data, our proposed model achieves much better performance than the baseline, which is based on resampling. When more microphone channels are available, the performance of the proposed model can be further improved, and it can still generalize well to a different sampling frequency. Next, we evaluate the speech enhancement performance on the DNS1 challenge data. Here we train all models on 16 kHz data and compare with the existing sorted models on the same dataset. We can see that the proposed non-causal model outperforms previous approaches in all metrics, which shows that it is a promising approach for both speech separation and enhancement. Finally, we evaluate the performance of a universal speech enhancement. To this end, we combine 5 commonly used corpora: voice bank demand, DNS1, Chime4, Reverb, and Whammer to form a large training and evaluation dataset. They cover a variety of conditions with different sampling frequencies, microphone configurations, and environments. We train our proposed model on the combined training data and always downsample the samples to 8 kHz for efficiency. Then we evaluate the model on each test data from different corpus with the original sampling frequency. Here we only show the average performance in all conditions, and more detailed results can be found in our paper. The EXCL result is obtained by training individual SE models on each corpus separately and evaluating them on the corresponding corpus. So this result can be regarded as a top line because the model is only required to fit a single domain. We can see that our proposed model achieves comparable performance with the EXCL results, while the variance of the metrics is consistently smaller, indicating that the proposed model is actually more robust by utilizing data from multiple conditions for training. The demo of enhanced samples and our implementations can be accessed through the QR codes. To summarize, in this work, we have proposed a single SE model the uses to handle multiple input conditions, including variations in sampling frequencies, microphone channels, signal length, and environments. We empirically show that the proposed model can be trained on a single sampling frequency, for example, 8 kHz data alone, and then tested on data with higher sampling frequencies. The proposed non-causal model achieves SOTA performance on DNS challenge data, and by combining 5 public corpora covering different conditions to train and evaluate the model, we show that the proposed model can achieve strong performance across all conditions. And we have provided our pre-trained model and code in ESP.NET. Thank you for listening. If you have any questions, feel free to contact me via email.